Good morning. I'd like to welcome everyone here and out at the NASA centers to our second aeronautics seminar in the Aeronautics Technical Seminar Series. Today's seminar is Crash Safety, Past Success, and Future Concepts by Dr. Karen E. Jackson. Karen has 25 years' experience as an aerospace engineer and currently works as a senior research engineer in Langley's Structural Dynamics branch. She received her bachelor's degree from the University of Tennessee and her master's and PhD from Virginia Tech. She is a resident expert in the topics of composite materials, structural design for energy absorption, and crash simulation, and has authored or co-authored over 100 technical papers. She has won numerous prestigious awards, including the American Helicopter Society's Harry T. Jensen Award and the H.J.E. Reed Award for Best Technical Paper at NASA Langley's Research Center in 2004. I am proud to introduce Dr. Karen Jackson.
Good morning, ladies and gentlemen. I'm very pleased and honored to be here to present the second ARMD technical seminar on the topic of crash safety, past success, and future concept. First slide, please. Let's see. Okay, this is just a short outline of my presentation. I'll begin by making a few introductory comments, try to give you a definition of what crash worthiness is. I'll describe test facilities that we have at NASA Langley and talk about some of the key elements of impact dynamics research, whether that research is applied to aeronautics or aerospace. I'll then give the objectives of the presentation, and basically those objectives are to focus on three areas. First is highlights of past full-scale crash test programs that have been performed at NASA Langley. I'll talk in detail about crash analysis. I'll present you a fairly novel deployable energy-absorbing concept that we have recently developed within our group. And then I'll conclude with some ongoing work and future plans. Next slide, please. The major goal of crash worthiness research, and again, whether it's applied to automobiles, aerospace vehicles, is to limit the dynamic decelerative loads that get generated during a crash that get transmitted to the occupants to either survivable or non-injurious levels. We do this by incorporating crumple zones, for example, in automobiles, and then in aerospace or airplane applications, we have energy-absorbing landing gear, subfloors, and seats. Now, the purpose of this crumple zone or crushable structure is to fail at a certain load and then to crush stably over a long period of time to dissipate kinetic energy. And I'll talk a little bit more about that in just a moment. Next slide. Here are some examples of automotive crumple zones. The automobile industry has been very forward-thinking in applying crash features to automobiles. Part of the reason for that is regulatory requirements. Part of it is that the market demands improved crash performance of automobiles. Automobiles have crumple zones. They also have frontal and side airbags. They have anti-skid brakes. They have a lot of features that are designed to protect occupants in a crash. Next slide, please. We also have similar features in rotorcraft and aircraft. For example, here I've shown a schematic drawing of a helicopter. There's a region between the floor and the outer surface or outer skin of the helicopter that's called the subfloor. And that region can be designed to absorb energy in a crash through controlled displacement. Next slide. This is what I mean when I'm talking about a crushing response. Essentially, you have a structure that's subjected to a compressive load. And what the ideal case would be is that the load response would increase to a peak load, and then at that point the structure would begin to fail and initiate a crushing response that's fairly stable over a long period of time. Now, if you take the area under that curve, that's the amount of energy that is dissipated or absorbed during the process of crushing the structure. Now, you're also going to hear me use a term called stroke. Stroke is very much a terminology that's similar to strain. Essentially, for this type of application, you have a structure that's subjected to compressive load. It deforms. You take that deformation, you divide it by the total original height of the structure, and then that's called the stroke. And then when you multiply that times 100, then you get percent stroke. So you'll hear me use that terminology, and I just wanted to make you familiar with what it means. Next slide. Okay, now we ask the question, what factors are involved in aircraft crash safety? And there are several important features and factors. The first is that we want to limit the loads that get transmitted to the occupants to survivable, non-injurious levels. The next is you want to provide a protective shell surrounding the occupant. And this is often very important for rotorcraft because you have a large rotorcraft, have large rotor transmission masses that are mounted above the occupiable area of the helicopter. During a crash, that mass can actually deform the structure that closes in on the occupants, and that's an undesirable situation. You also want to provide a secure tie-down of the occupants using seats, restraint systems, so that the occupant doesn't become a projectile inside the cabin of the aircraft. You want to eliminate post-crash fire hazards, and this has essentially been done for most rotorcraft, especially military rotorcraft, using crash-resistant fuel systems. You want to provide for emergency egress. You want to mitigate head strike potential, and again, this is a challenge for rotorcraft because you have cyclic control sticks that are in the way when the occupant flails or the head fall comes forward, can be a head strike potential. And you want to do all these things while minimizing the cost and weight penalties associated with crash. Next slide. Okay, now I have a schematic that shows sort of a before and after. And you see the occupant sitting there in a sort of a GA aircraft, and he has available to him a certain distance that can be used to absorb energy. He has landing gear that can stroke, he has a subfloor that can crush, and he has load-limiting seats. So the ideal situation for crash-worthy design is that it's accomplished using a systems approach in which all of the features that are in the aircraft can be used to absorb energy and dissipate kinetic energy of impact. And so you see the after condition, the landing gear is stroked, the subfloor has crushed, and the seats have deflected, and the occupant has been decelerated in a controlled, stable manner, and then we have a survivable impact. Next slide, please. Okay, now I'm going to switch gears through with definitions. Now I'm going to talk about facilities. I work at a very unique facility. It's called the Landing and Impact Research Facility. It was recently renamed. We call it Lander now. It's a steel A-frame gantry. It's about 240 feet high, about 400 feet long, and about 265 feet wide at the base. It was constructed during the early 1960s, has a lifting capacity of about 30,000 pounds, and during the late 1970s, we added a 70-foot vertical drop tower under the northwest leg of the gantry, and that was added for doing vertical drop tests of fuselage sections. Okay, next slide. Now, the facility wasn't originally built as a full-scale crash test facility. As I mentioned, it was built in the early 1960s, and it was originally built as a lunar lander research facility. And as such, it was used to allow the Apollo astronauts to train for the last 150 feet of descent onto the lunar surface. And this was used for this application from 1964 until about 1970. Using a tethering system, we could actually simulate the 1/6 gravitational environment of the moon. Because of its significant role during the Apollo program, the facility was awarded a National Historic Landmark in 1985. And so you see a picture there of the gantry. The surface underneath the gantry was cratered to look like the surface of the moon. The astronauts would actually climb into the lunar excursion module and then practice lunar landings. And I have a short video to show you here of one of those practice runs. Okay, next slide, please. Okay, as the Apollo program was coming to a close in the early 1970s, the facility was converted into a full-scale crash test facility. And during the 10-year period from 74 until 83, we had a very active general aviation crash test program. I'll discuss that a little bit more later. Also, in the late 70s and into the early 80s, we were starting to look at crashworthiness of transport aircraft. And that test program culminated with the full-scale remotely piloted crash test test of a Boeing 720 that was performed out at Edwards Air Force Base and NASA Dryden. In the 1980s, early 1980s, the focus of the program was shifting from looking at metal aircraft to looking at composite materials. And the focus of the research program was to use a building block approach to see how we could incorporate energy-absorbing concepts into crash-worthy composite aircraft. We looked at crushing subfloor concepts, we looked at frame-stiffened designs, eventually fuselage sections, and then the technology has matured to the point where we've done full-scale crash testing of all composite general aviation aircraft and rotorcraft. Next slide. And finally, I want to talk about some of the key elements of impact dynamics research. Essentially, the goal of this research, of any research program that has an element of impact dynamics, is to develop a fundamental understanding of the crash response of aerospace vehicles. And then once we understand the response, then we can look at ways to improve the crash performance of that particular vehicle. Essentially, that is like a stool, and we have 4 legs supporting that stool. The first is full-scale crash testing. We have this unique facility. We need to perform testing so that we can understand the physical phenomenon associated with crash. We also have done quite a lot of work in impact simulations using analysis tools, and I'll talk quite a lot about that in just a few moments. We often have to look at development of innovative concepts for crashworthiness applications. And then the final key element is dynamic materials testing. Often if you go to a handbook, you can find stiffness properties, you can find yield properties, you can find ultimate failure strain, but you often will not find how that material behaves under dynamic loading. And so consequently, we have to do the testing to generate the information that's used in our analytical simulations to improve the correlation that we have. Okay, next slide. All right, objectives of the presentation are to focus in 3 areas. I'm going to talk about some of the past full-scale crash test programs that have been performed at the facility. This is sort of fun. You get to see videos, and I hope you enjoy it. Then I'll talk about crash analysis, and then finally I'll talk about development of an innovative concept for crashworthiness that has recently been developed and has both application to aerospace and aeronautics. Next slide. Okay, as I mentioned before, back in 1974, NASA entered into agreement with the FAA and the GA industry to look at the crash performance of general aviation aircraft. And the objectives of the program were to determine the dynamic response of the integrated system, the airframe, the seats, and the occupants. We also wanted to look at the effect of varying flight parameters on the structural damage that occurs during impact. And we looked at failure modes of seat restraint systems and seats. Now, the program also included a lot of work that was done in the background on development of analytical simulation tools, test data evaluation, and structural concept development. And during this 10-year time, we actually tested performed 33 full-scale crash tests, mostly of Piper aircraft, particularly Navajos, Aztecs, and Cherokees. Next slide. Now this slide shows a schematic of the gantry, and I'll discuss how the facility is used for performing full-scale crash testing. Essentially, you see an airplane that's suspended from the gantry. There are a set of cables that are attached to an aircraft harness, and by adjusting the lengths of these cables, we can get pretty much any roll, pitch, or yaw attitude that we want. Then the harness is actually tied to the gantry through swing cables and pullback cables. So we pull the aircraft back, we release it, and then it comes to the ground, and about maybe 3 to 4 feet above the ground, all of the cables are pyrotechnically separated from the aircraft so that when it hits the ground, it's in free flight conditions. And we often have quite a lot of instrumentation on these tests, typically on the order of between 100 and 200 channels of data, typically collected about 10,000 samples per second. We have a lot of external cameras, video cameras, high-speed film cameras, and we have cameras on board to see how the seats are responding and the occupants. I think that's about it. Let's go on to the next slide. This slide shows a montage of some of the tests that were performed during this 10-year period of time. You can see we tested high-wing aircraft, low-wing. We tested some fairly shallow impact angles, and some were fairly steep. We tested onto dirt and onto concrete. So we were really looking at this as a landmark study. It was used to establish what is a survivable envelope for crashes of these type aircraft. And this is important because most of the fatalities and injuries that occur upon a crash of GA aircraft occur because of the impact itself, because these aircraft don't carry enough fuel to have smoke and fire as a major cause of fatalities and injuries. Next slide. Okay, as I mentioned, back in the 90s, and this is when I sort of came on, back in the 80s, beginning of the 80s, the shift of the program focused from looking at metal aircraft to looking at composites. And this technology, as I mentioned, is matured to where we've done full-scale crash tests of a number of all-composite aircraft. Beginning in 1994, we did the first crash test of Learfan. Just to let you know, the Learfan was the first all-composite aircraft to attempt FAA certification. Unfortunately, it failed certification, and the company, Learfan, went into receivership, and we were able to purchase 2 of the aircraft for crash testing. The first test was in 94. We did a second test in 99. Now, the first all-composite aircraft that did get FAA certification was the Beech Starship, and we did a full-scale crash test of that aircraft in 1995. And then in 96 and 97, we did crash tests of the modified Cirrus SR-20. This is the same aircraft that was recently involved in a crash into the residential tower in New York that I believe Corey Lydell was actually flying. And then in 2001, we did a crash test of a modified Lancer. And I'll tell you a little bit more about these in just a moment. Next slide. Okay, now we're going to show you a video of the 1999 full-scale crash test of a modified Learfan aircraft.
2, 1, release.
You see, these tests actually generate a lot of interest. A lot of people show up. They get very excited. They are very interesting to see. I mentioned that this aircraft is modified. As I mentioned before, we have 2 of these aircraft. This aircraft was made mostly out of graphite epoxy. It was extremely stiff. It had very stiff composite stanchions in the subfloor. So because we had 2 aircraft, we decided to do the first test in the baseline configuration. And the second test, we actually removed the composite stanchions in the subfloor and replaced them with a composite energy-absorbing subfloor of our own design. We also put in load-limiting seats. Both aircraft were tested for the same initial impact, but this aircraft actually had a secondary impact into a plywood barrier, and the reason for that is because we had side-facing seats. We wanted to introduce a longitudinal pulse to evaluate the response of the seats and the occupants to that longitudinal input. Okay, next slide. Okay, now you're going to see a full-scale crash test of a modified Lancer. And this is a very spectacular test. It was performed at 96 feet per second, which was a really high impact velocity. You'll notice several things happen during the test. First is the tail falls off. The wings also shear off. The engine falls off. And the purpose of this is a term we call mass shedding. As you dump mass, you lessen the kinetic energy of the impact, and you don't have to dissipate that energy if the mass is then removed from the aircraft. So this is a common feature that you'll see in some of these tests. Again, this was a very high impact velocity that we did, and this test was done in support of NASA's AGAT program, Advanced General Aviation Transport Experiments. Next slide. Okay, so what was all the big deal about all this crash testing? First of all, as I mentioned, that was a landmark study. Before the GA crash test program, we did not know what a typical acceleration pulse was for a survivable crash of a GA aircraft. Now we know. And then that information was used to establish seat criteria that's used by the FAA today for certification. We were also able to look at occupant data and compare that data with known human injury criteria and to assess the survivability of a particular crash. What we found from the early crash tests of composite aircraft is that the acceleration levels were much higher than comparable metal aircraft. Then as later aircraft came along, we found that minor improvements like that energy absorbing subfloor, load limiting seats, significantly improved the crash performance of these aircraft until they were in some cases superior to comparable metal aircraft. Next slide. Okay, now I'm going to switch gears again and talk a little bit about some of the support testing that we've done in support of the DoD. Because we have this unique facility, we often get asked to perform testing in cooperation with the DoD to evaluate various different configurations that they have. I'm only going to focus on 3 tests, one for the Navy, one for the Air Force, one for the Army. But you can see from this list that we have a high preponderance of doing tests for the Army. There are several reasons for this. One is the fact that the Army's Aviation Applied Technology Directorate is located very close to Langley. They had a mission for safety and survivability and brought many of these tests to us. And also the testing is very compatible with the existing programs that NASA was also running. Next slide. Okay, for the Navy, we did actually some static and dynamic tethered hover tests of the XFE-12A. This is a prototype aircraft that was a VSTOL aircraft intended to take off vertically and then fly from vertical hovering. These tests were performed in 1978, and essentially following 6 months of testing, there were some deficiencies found in hovering flight. The cables that were used to support the aircraft had a load cell that was put in series with the cables, and essentially that load cell never read 0 load, which meant that the aircraft wasn't even supporting its own weight. Consequently, that led to the Navy's decision to cancel the XFE-12A program. There's a short video here, and I'll let you watch that. Okay, let's move on to the next slide, please. Okay, we were asked to perform numerous tests in support of the Air Force for the F-111 crew escape module. When this aircraft gets into trouble, the entire crew module that you see in the photograph there is detonated away from the aircraft. It comes down on a parachute, and it has an energy attenuating airbag system that has blowout plugs. Turns out that the Air Force was experiencing a lot of back injuries and spinal cord injuries when this aircraft, upon landing of this particular crew module. So they came to us and asked us to perform testing for them, and we did that. Basically, as a result of the test program, the Air Force was convinced to add energy-absorbing seats into this airframe, and they made some modifications to the bag design and the blowout plugs. When I say we tested numerous times, probably between 60 and 70 tests, and go ahead and show the video, and you can see how the airbag system just actually didn't work like it was intended. Interestingly enough, the facility is being geared up at this very moment to evaluate external airbags as an energy dissipation mechanism for Orion or the crew exploration vehicle. So it should be interesting to see how that works out. Next slide. We performed a number of tests to qualify the wire strike protection system for 8 different Army helicopters. It turns out that the helicopters, when flying close to the ground, nap of the earth is what they call it, the biggest hazard to them are wires. Whether they be telephone wires or power cables, whatever they are, they can bring down a helicopter pretty quickly. And so a passive device was developed called a wire strike protection system. Essentially looks like a pair of scissors. They're placed on top of the airframe and on the bottom of the airframe. And the plan is that when the airframe hits a cable, then the cable is supposed to go either up and get caught in the top cutter or go to the bottom and get caught in the bottom cutter. Then the cable is nicked and it just fails in tension and does not bring the helicopter down. And so for these tests, what we did was we actually pulled the helicopter back and just allowed them to swing into a 3/8-inch steel cable. Now for the first video you're going to see is of a AH-1 Cobra helicopter. The view is from the top. We've got a camera looking. You're going to see the helicopter approach the wire. There it is. It hits the front of the fuselage and then goes up and gets caught in the top cutter. And if you're viewing this from afar, you don't even notice that the helicopters hit anything. It just works beautifully. Now you're going to see an example where it didn't work so beautifully. This is a test of an OH-6. You're going to see an external view, and then it's going to switch to inside. You see the cable approaching, and it turns out that the support frame for the canopies wasn't strong enough to force the cable to go up or down, and instead it buckled that support frame, and consequently the cable cut right through the helicopter, as you can see. But these devices have proved very effective. They're now installed fleet-wide on all military helicopters and in most commercial helicopters. So a very successful test program. Next slide. Okay, now I'm going to switch gears again and talk about crash analysis, a topic that's very near and dear to my heart. I spend a lot of time in front of a computer doing this work. And I put a little sort of an outline chart here just to tell you about what you're going to see. I'm going to describe the crash analysis codes that we use. I'm going to talk about some results that came from a NASA workshop that was held back in 1992. I'm going to show you an example of validation of numerical simulations. This was a research program that was done in the late 1990s. And then I'm going to talk about probabilistic analysis and uncertainty quantification, some examples of crash test analysis correlation that have been performed since 2000 to the present time. We'll talk about support to the shuttle return to flight program that's been done in analysis, impact analysis, and also the analysis support we're providing now for landing and descent phase of Orion. So a lot of work here, and I hope this is interesting to you. Next slide. We have used in the past codes like MSC Dytran and codes like LS-DYNA. There are also codes PAM-Crash and Radios and Abacus Explicit, and these codes can all be used for transient dynamic simulations. Interestingly enough, they all have as their parent code a code called DYNA-3D, and DYNA-3D was a public domain code that was developed under Department of Energy sponsorship. It was developed at Lawrence Livermore National Lab, and it was initially released in 1976. And then constant improvements were made, and it was released again in later years. But because it was a public domain code, various commercial vendors obtained it. They added extra features to it, changed it a little bit, and then you see these commercial spin-offs. Because these codes have a common parent, they have a lot of common features. These include contact impact algorithms. Some of these are very complex. They have highly efficient element formulations. The codes wouldn't run without very simple but efficient elements. We have hundreds of material models that are available. Most of the codes have some type of coupled Lagrange-Euler capability for doing fluid structure interaction modeling. Multiple constraints are available, and the codes allow input of initial and boundary conditions. Next slide. Now this sort of shows how the explicit time integration procedure is done, which is the basis of most of these codes. We use explicit time integration. And I'm not going to go through all the details, but several points I want to make. First of all, nowhere does the code create and repetitively decompose a large global stiffness matrix. And this is important to understand. Most structural analysis codes, such as NASTRAN, they do that. These codes don't. Also, a key feature of the codes is the time step. The time step is determined by the time it takes a stress wave to cross the smallest element face in the model. And so it's very important to not have extremely small elements in these models, because time steps can be on the order of a microsecond or less. And as the time step goes down, the time to run the simulation gets much, much longer. It's also interesting to note that for most structural analysis codes, as the complexity of the model increases, more and more elements, the time to run them increases exponentially. For these codes, as the model increases, the time to run them increases essentially linearly with added elements. So that's an important feature to understand. Next slide. Now for the example that I'm going to show you in just a moment, we're going to be using a code called MSC Dytran. And again, it had a parent. Its parent was DYNA-3D. The code is marketed by MSC Software. later on, they actually purchased a code called Pisces, which is an Eulerian code to allow MSC Dytran to have the Euler-Lagrange capability. They also made the input deck as compatible as possible with MSC Nastran. And so that is an important feature, because if you're familiar with Nastran, then when you look at an MSC Dytran deck, you say, oh, I understand what this is, because I'm familiar with it. So it has fairly widespread application within the aviation community. Next slide. So, as I mentioned, I think I mentioned this, that NASA has had a long history in sponsoring development of crash impact simulation codes. In fact, back in the 70s, NASA sponsored development of a code called DICAST, Dynamic Crash Analysis of Structures, which had both implicit and explicit time integration. Back in 1992, we held a workshop, brought a lot of industry people there, brought a lot of experts in code development and use of the codes together for this workshop, which is called Computational Methods for Crashworthiness. And during the workshop, which was a very good workshop, we had a panel discussion. We asked the experts, what are some of the identified computational needs for crashworthiness? And we came up with a lot of answers, and these were essentially grouped into 5 categories. First of all is that we have to understand the physical phenomenon associated with the crash. What happens during a crash to the structure? And often there's the initial impact, and then often there's a secondary impact. And sometimes it's the secondary impact that's more important than the initial one. You don't know that until you do a test. We also had to develop, or need to develop, high-fidelity modeling of the occupant and the vehicle. And since this workshop, models have gotten more and more and more complex, and I'll talk about that in just a moment. We also have to have efficient computational strategies, and we rely heavily on test methods to generate data for input into these simulations, as I mentioned, for materials modeling. And then finally, validation of numerical simulations. Essentially, the word was that we will not use these codes for design, during preliminary design, until we have confidence that the results that are coming out of them give us accurate results, so that we have this confidence level. We'll then use the codes for design. And so the goal of that was to do these numerical simulations, do the test analysis correlation to build that confidence. Next slide. To that end, back in the late 1990s, a research program was initiated to specifically look at the capabilities of commercially available transient dynamic code, in this case MSC Dytran, in predicting the response of composite prototype helicopters subjected to impact loading. There were 3 main parts of the program. The first was to do the crash test of a composite prototype helicopter with the goal of generating test data specifically for the purpose of correlating with analytical data. We had to develop the model of the test article and run the simulation, and then the third component was the test analysis correlation to then validate the numerical simulation. So you're going to hear about each one of these pieces. Next slide, please. This is what the test article looks like. This is actually at the moment of impact. The test article was the Sikorsky Advanced Composite Airframe Program Helicopter, or ACAP. I have to step back just a minute to give you a little history. The ACAP was a program that was sponsored by the Army. It was initiated in the 1970s, and the intent of the program was to try to encourage the airframe manufacturers to use more composite materials in their design. They awarded 2 contracts, one to Bell, one to Sikorsky, and they asked that they build a composite helicopter made primarily 80 to 90% of composite material, and that the helicopter would meet all of the military requirements, what I call the ILITs, manufacturability, durability, reliability, and survivability. And at the time, survivability was determined by the MIL standard 1290, which was a requirement that said that the helicopter and occupants had to survive a 42 foot per second vertical drop test, as well as a 27 foot per second forward component, which had a resultant of 50 feet per second. Okay, the way Sikorsky met that requirement was by putting most of their energy dissipation in the main landing gear. So this aircraft had very sophisticated landing gear. It also had a crushable subfloor. When we actually got the test article, it had been in storage for about 10 years at Fort Eustis, Aviation Applied Technology Directorate. So, and when we got the aircraft, it did not have the original nose gear. So we had to put in a non-crash-worthy nose gear and try to retrofit it to improve the crash performance of the nose gear. We also had to make some modifications to the main landing gear. The impact conditions for the test were 38 feet per second vertical, 32.5% feet per second forward velocity, and that has a resultant of 50 feet per second, which is the same as the mill standard. We also induced a 9.6 degrees per second pitch angular velocity, and you can see the helicopter here at the moment of impact. We actually impacted with a 6.25 degree nose up pitch and a 3.5 degree left roll down. So it hit with the left main gear first, then the right, then the nose gear. And you'll see that in just a moment. Next slide. This just showed that we had anthropomorphic dummies on board. We had 2 crew, a pilot and a co-pilot, and we had 2 troop occupants. The pilot was a hybrid 2 male occupant, weighed about 170 pounds, and the co-pilot was a hybrid 3 occupant and weighed about 198 pounds. He also had a 7-pound helmet on board. Both of these occupants were seated in load-limiting seats that were commercial seats used for the Black Hawk. The troops were seated in ceiling-mounted wire-bender load-limiting seat. I'll just point out to you that in helicopter lingo, the pilot sits on the right side, the co-pilot sits on the left side. So if I say right and left, you'll understand the pilot's on the right and the co-pilot's on the left. Next slide. Okay, now I've got 2 videos that showed what happened during the crash test. So you can go ahead and play the one that shows overall version.
3, 2, 1, release.
Okay, so that was the overall. Now you can see the video that shows a close-up of the dummies and a little bit more detail about what happened during the test. Essentially, after this crash test was performed, we did a complete occupant assessment to look at whether these occupants survived this test. Our general assessment was that this was a survivable test. However, probably you would have seen some injuries. We did this by looking at things like lumbar load. We don't want the lumbar load to exceed 1,500 pounds. That's the limit for non-injurious conditions. We also looked at the dynamic response index, the Brinkley index, and we looked at whole body acceleration with comparison to the I-band curves. So we've done complete occupant assessments. This is important because we're doing the same kind of work now to assess impact survivability for Orion and the crew exploration vehicle. Next slide. Okay, this is post-test picture. You'll know that tail cone has deflected. The tail cone was actually designed to fail. It didn't completely fail and separate, but it was designed to do that. You'll also see a sequence of events. Essentially, time equals 0 is the point of left gear touchdown, main gear touchdown. The next thing that happens is the right gear touchdowns, then the nose gear touches down, and then at 0.1 seconds is when the fuselage hits the ground. And essentially by 0.15 seconds, the main impact is essentially over. This is important to remember because this has implications for the analysis. Essentially, the major part of the impact occurred with just the landing gear deforming, and the fuselage is just sitting there providing bulk weight. And so this had influence with the simulation. Next slide. Also, I wanted to point out the importance of load-limiting seats. So what you're looking at are pilot vertical acceleration data and co-pilot vertical acceleration data. The blue channel is the floor-level vertical acceleration near the pilot seat, near the co-pilot seat. The dashed red response is the seat pan acceleration. The dashed green response is the chest acceleration in the vertical direction of the pilot and the co-pilot. For the pilot, you'll see that the peak acceleration at the floor is about 95 Gs. The effect of that load-limiting seat was to reduce that acceleration down to about 40 Gs for the loads that get transmitted to the occupants. This is very important, 55 G differential. Now, if you look at the co-pilot, the maximum acceleration peak is about 90 Gs, and then that got reduced to about 35 Gs. Again, a differential of 55 Gs. Very important to have limiting seats. Otherwise, that floor-level acceleration would have been input into the occupant. Instead, it was reduced by 55 Gs. So very important. And I know that people are now working on looking at seating systems for Orion. This is very important. Next slide. Okay, now I'm going to talk about analysis. Here is the model we started out with. This was a Nastran modal vibration model that was developed during the DAM Vibes program. It was a very complex model at the time. You'll notice it had about 10,000 elements, very small by today's standards. It also had about 200 different material models representing the composite properties, the composite laminates used to manufacture this airframe. We had the task before us was to translate or convert this Nastran model into a Dytran model and then run the impact simulations. Next slide. Now you're going to see a detailed photograph or a picture of the subfloor model and also a picture of the actual pretest picture of the subfloor in the aircraft. Now this aircraft had a very unique subfloor. It was a beaded web design. The top portion that you see was made out of graphite epoxy. That portion of the subfloor was not designed to crush. It was intended to react the loads of the crushable portion and to provide a stable platform for the seat and occupant restraints. The crushable portion was a 4-inch beaded panel made out of Kevlar that you see at the bottom of that photograph. We had to take the Nastran model, rediscretize it so that we could predict that crushing of that lower portion of the subfloor. Next slide. This is some of the various components in the model. There were quite a number of beam and rod elements. There were quite a number of triangular elements and quite a number of quad shell elements. Generally, we don't like to use triangular elements because they're generally too stiff to run in these explicit simulations. But for this case, we had to start with the Nastran model, and that was what sort of tied our feet to it. Next slide, please. Now, the landing gear response. The landing gear was very complicated. As I mentioned before, Sikorsky designed the landing gear to take out 80% of the impact requirements for the mill standard. It's a 50 foot per second impact. And the way they did it is they had a 2-stage model, or landing gear. They had an oleopneumatic phase that's about 12 inches long, and then this was supposed to handle sort of hard landings, or student landings. And then if they had an impact landing, a shear pin would break, and then you would gauge a crushable honeycomb stage, which was about 25 inches long. You'll notice that when the gear is fully extended, it's about 12 degrees rotated from vertical. During an impact, the gear actually deforms upward and rotates outward. And so it has a very complex response. And the question was how best to model this with our MSC Dytran code. Turns out what we used was a kinematic model. We used beams and springs and masses to basically predict both the oleopneumatic phase and the crushable honeycomb phase. Turns out an external subroutine was written to calculate the nodal positions and velocities, and this was used to represent the landing gear responses. We had a very complicated guide mechanism for alignment, and then the nose gear was just simply modeled with using a spring element. Next slide. And this is our MSC Dytran model. Not a whole lot different from the previous model. You see we have an impact surface, we have modeled landing gear, and the total number of elements is now down to about 6,600 elements. Very simplistic model for the time. Remember, this was done between 1997 and 1999, so this is a while ago. We reduced the number of material properties from 200 down to about 29 material properties. So this was a challenge. I want to stress here that this was not an easy conversion. It took 3 of us working about 6 months just to convert the model from Nastran to Dytran, and then again a few more months to take the Dytran model and get it to where it would actually perform like we wanted it to. So it took a lot of effort to get from where we were to this point. Next slide. Now, one of the things we had to do was to handle that landing gear response. If you remember, from time equals 0 until 0.1 seconds, really the only thing that's involved is the landing gear. The fuselage is just sitting there with the exception of the tail cone. So what we did was we decided to implement a 2-stage modeling approach. During the first 0.045 seconds of the simulation, the fuselage section itself was modeled as using rigid material properties. And then at 0.045 seconds, all of the nodal positions and velocities were printed out to a file, and then this file was used as input to the flexible simulation, which was run until the end of the simulation at 0.15 seconds. And there were several reasons for doing this, and I'll go ahead and talk about that in the next slide. The first advantage is that this simulation approach provided a really efficient means for us to evaluate the landing gear response. It also allowed us to input the pitch angular velocity, which wasn't possible at the time using the flexible approach. It also reduced significantly the amount of CPU time it took to run the model. We went from having to run it over a day, 18 hours, to down to about 9 hours, so we could run it overnight. This was important. The disadvantages, however, is at the point where we transitioned from rigid to flexible, the landing gear forces were quite high, on the order of several thousands of pounds, and those were input impulsively and instantaneously into the flexible model, and so it generates some high oscillations. We tried some approaches to dissipate those, were really never really completely successful, and because we were modeling the fuselage as a rigid model, we weren't able to capture completely the tail cone dynamics. So you'll see that in a moment. Next slide, please. Okay, now I'm going to talk about test analysis correlation. Really, we look at several things. First of all, we try to look at kinematics. Do we get the time sequence of events correct? The next thing is, do we get the discrete failures that occur? Do we model those accurately? And then the third is, do we correlate well with the acceleration data that we obtain from accelerometers and other instrumentation on board? So correlation of time sequence events, we essentially captured that very well. It's maybe a little difficult to see, but we actually got, at the time of left gear contact, then right gear, then nose gear, the time of some of the major things that occur, for example, transitioning from the oleopneumatic phase to the crushable honeycomb phase in the landing gear. These were actually very well predicted. Next slide. It turns out that at the point where the structure is that supports the overhead rotor transmission mast, they have a very beefy bulkhead in that structure, and they also have two beams that support and provide extra support to prevent the overhead mast from coming into the fuselage during an impact. And you can see a picture there of what those two frames look like, and the model, the undeformed model. During the simulation, we actually predicted the discrete failure of one of those beams. And this was done using a very simplistic failure model in the modeling of the composite failure using maximum strain. So not a very sophisticated composite failure model, but we were able to predict failure of that beam. Next slide. We were also able to predict crushing of the subfloor. Crushing was localized to a region near this bulkhead at body station 188. We were able to predict crushing. Turns out that the height of the crushable structure was about 4 inches. It only crushed during the test about 1 inch, and that's about what we were able to predict. Next slide. Now I want to show you some, this is sort of where the rubber meets the road, predicting these acceleration responses. But what you're looking at here is not acceleration, it's a velocity. We took the acceleration data, integrated it to get velocity. And often we can determine a lot more about what's going on in the test article by looking at velocity as opposed to acceleration. So what you're looking at is the co-pilot floor first. And the experimental data is shown in the solid blue line, and the analysis is in the dashed red line. And the first thing that you'll notice is that between time equals 0 and time equal 0.1 seconds, no velocity has been dissipated out of this system. It's essentially held constant. And so we actually predicted that fairly well, but you'll notice that at 0.045, we transitioned from the rigid model to the flexible model. We introduced some oscillations, and that's why you see that response there. And we also over-predicted the rebound, but in general, we correlated fairly well. Now at the top of the right gear, we see a very different response. From the time equals 0 until 0.1 seconds when the fuselage impacts, velocity is being removed from the system. And we predicted that very well. You'll also notice that at 0.05 seconds, there's this sort of oscillation in the experimental response. This is actually the point at which that shear pin fails and you transition from the oleopneumatic stage to the crushable honeycomb phase. And it introduces an oscillation, and we saw that and we were able to predict that fairly well. Okay, now let's look at some acceleration plots in the next chart. We're going to look at an accelerometer that was located near the pilot's seat and an accelerometer that was looking at located on the floor near the co-pilot's seat. And what you see in this correlation, and this is filtered acceleration data, is that we We over-predicted the peak. We didn't actually predict the timing of the peak that well, but in general, when you look at it and given the technology at the time, we look at this and we say, hey, we were in the ballpark. We did pretty good. Next slide. Now you're going to look at acceleration traces for the right engine and the left engine. In this case, for the right engine, we absolutely predicted the peak acceleration very well, but not the timing of the peak. And then for the left engine, we predict the timing of the peak, but not the magnitude of the peak. Okay, next chart. So what were some of the lessons learned from this exercise looking at test analysis correlation? First of all, we had difficulty in converting a static model into a dynamic model. And I dare say we would have the same difficulties today. Maybe it would be a little easier. I hope so. We also stressed the importance of conducting an integrated simulation in which we had a kinematic model of the landing gear and a finite element model of the fuselage section. We also did not use very sophisticated failure models for composites. Now we have much more sophisticated failure models for composites. But at the time, we had max strain, and that's what we used. So it is fairly difficult to model initial and progressive failure composites. We also had some difficulty in inputting our initial conditions. We also had issues with meshing and element selection. And finally, you heard me use terminology in describing the test analysis correlation of we were in the ballpark. We sort of talked about magnitude of the peak acceleration, timing of the peak, the pulse duration. These are qualitative assessments of correlation, and we really needed to look at quantitative assessments of correlation to build confidence in the use of these codes. And so we needed to look at uncertainty quantification in both the analysis and the experiment, look at improved correlation methods, and particularly look at probabilistic analysis. Okay, next slide. We actually have done some work in this area of probabilistic analysis and uncertainty quantification. We did a vertical drop test of the test article shown in the photograph. This was a composite fuselage section that was specific. The test was specifically performed to quantify experimental uncertainty. By that I mean that it was instrumented with accelerometers that were located in symmetric positions. It was instrumented with accelerometers that were located together so that we could compare responses. And what we found was what we thought was a completely vertical impact actually had a 1-degree pitch. And so we had to account for that 1-degree pitch in the simulation in order to get good test analysis correlation. We also have used probabilistic analysis methods. This is used to bound the modeling and experimental uncertainty, to identify parameters that are controlling the uncertainty, and to optimize the structure assuming uncertainty in the parameters. Next slide. Okay, since the late 1990s, we've had plenty of opportunities to look at test analysis correlation using analytical methods. Essentially, we've more or less switched from using MSC Dytran to using LS-DYNA, and we've performed simulations of transport aircraft, fuselage sections, full commuter aircraft. We did testing and analysis support for the Mars Sample Return Earth Entry Vehicle. We've done integrated simulations with human occupant models incorporated into the finite element model of the structure and also fluid structure interaction. Next slide. The expertise that we gained through all of this test analysis program was used to support the Columbia Accident Investigation and the Return to Flight program. The team at NASA Langley worked in cooperation with other research centers, NASA Glenn, also Marshall. We worked in cooperation with Boeing Philadelphia, Southwest Research Institute to really focus on the problem of determining the threshold of damage to the shuttle wing leading edge panels for impact of various debris sources, including foam, ablative material, ice, other debris including tile putty, gap filler, on and on. Focusing early on, we were trying to look at what the impact scenario that brought down Columbia might have been, looking at, for example, there's a photograph of the test that was performed at Southwest Research Institute looking at foam impact onto panel 8 and the simulation using LS-DYNA. It was very important for us to do material strain rate testing so that we could determine material properties of foam and ice and all these different debris sources so that we could input that information into our simulations. Next slide. And currently we're actually supporting the landing and descent phase of Orion by doing quite a lot of simulations. Initially we were looking at rigid body models, trying to look at the outer geometry, the mass, the center of gravity, doing stability analysis during impact, what impact conditions would cause tip over or rollover of the article. And then now we're looking at flexible models, and then we hope that that will continue to where we actually look at an integrated, fully flexible model of the command module that includes dummies, seats, restraints, and any external energy absorbing devices that might be used. Okay, let's switch gears now and go on to another topic. Next slide. Okay, this is my final topic. Basically, I wanted to talk about development of novel concepts. And the novel concept that I want to talk about is a deployable, externally deployable, energy-absorbing concept that looks like composite honeycomb. And that's really what it is. The key feature, however, is this unique flexible hinge design that allows the honeycomb to be stored at flat and then deployed either linearly or radially to give us the energy absorber that we need. The structure can be optimized or tailored through the choice of cell geometry. You see here a square cell and then also a hexagonal cell. We can use different materials. To date, I think we've looked at fiberglass, epoxy, spectra, and Kevlar. We can modify the cell geometry, the wall thickness, and tailor the response that we want. Next slide. This shows some of the deployment mechanisms that can be used. We can use pneumatic deployment, mechanical deployment, or hydraulic deployment. The section can be deployed linearly or it can be deployed radially, as shown there. I will mention that this concept is very lightweight and very structurally efficient. It weighs about 1.1 pounds per cubic foot. This is typically the weight that you would expect to see for some structural foams. So it's an extremely lightweight material. Next slide, please. Okay, because of its unique properties, we saw potential applications of the concept for both, for all of these items that are listed here, but I'm going to focus on helicopter crashworthiness and landing system for a crew exploration vehicle. Next slide. Okay, we thought that the concept could be used in a radial fashion to provide energy absorption for landing of the Orion concept. This is just one of many concepts that have been evaluated. There are other concepts, airbags, other landing systems that have been looked at, so this is just one of many. I want to show you a short video that illustrates how the deployment might be accomplished, and you can see that here. Of course, in the work that we're doing in simulation, we're actually performing trade studies to evaluate all of the concepts, and this one was modeled, and you see LS Dyna simulation of the deployed concept, and that's a video, very short. This was about a 40 foot per second horizontal with only a 5% foot per second vertical simulation. Next slide. Now, this concept has some attractive features for aerospace or aeronautics applications. And what you see here is a plot of crush stress versus crush stroke for this concept. It was designed for 30 psi crush. You'll see the blue line is sort of the actual data. It has a lot of noise in it, and then you filter it and you get this response. We got an excellent energy absorption behavior up to about 70% stroke. The concept has very high specific energy absorption capabilities. By that means it has high energy absorption and low weight. It has superior shear rigidity, large stroke. It seems to be independent of the impact surface, and also it seems to be strain rate independent. So it looked very attractive for aeronautics applications. Next slide. This chart just shows, or this video shows how this concept might be deployed on a helicopter. This is not a real helicopter. This is just a graphics, but it just shows how it might be accomplished. Okay, so I mentioned that the concept looked attractive for energy absorption in aeronautics applications. Next slide, please. So we decided to see if we could test it in a vertical drop test of a composite fuselage section. We added 4 of these deployable structures to the floor, bottom floor of this fuselage that was loaded with 10 100-pound lead weights to simulate floor loading. We pulled the section up to about almost 25 feet, which is pretty high, and dropped it vertically and got an impact velocity of about 38.6 feet per second, which is really pretty severe. And here you see a post-test photograph, and you can see that the deployable structure has deformed and crushed. Looks like what old Coke cans used to look like when they crushed. Next chart, please. Okay, this is a short video of the test.
3, 2, 1, release.
Okay, and what we found out after the test is we saw no visible damage to the upper section of the fuselage or the floor. Also, the average accelerations at the floor about 18 Gs. This is phenomenal for this application and a significant improvement over previous designs. We also found out that 93% of the kinetic energy of the impact was dissipated by crushing of the subfloor. And the subfloor crushed about 14.5 inches. The original height was about 20 inches, which gives us a 73% stroke. So it's an excellent example of this concept. Next chart. Okay, now I'm going to conclude just by telling you about ongoing work at our facility. We are providing quite a lot of support for Orion and Constellation. The facility is being used to evaluate various landing concepts. As I mentioned, we're now looking at airbags. You're going to see a short video of one of those tests onto soft soil. And that's the top.
3, 2, 1, release.
This again has a large forward velocity and not a very high vertical velocity. We're impacting into soft soil. And this is the 1/2 scale sort of rigidized concept that we're doing initial testing on. We also have some facility upgrades we're planning. We're getting a new elevator, so we don't have to climb 22 stories to get to the top. And analytical work continues to be performed in conjunction with the testing. And we hope to have a fully flexible integrated model. And by integrated, I mean seats, occupants, restraints, external energy absorbing devices, and the flexible model of the aircraft as time goes on. Next slide. Of course, I'm doing quite a lot of work on fundamental research in subsonic rotary wing. And our research plans are basically to do multi-terrain evaluation of our energy-absorbing concept and to do correlation with analysis. We want to look at more detailed parametric studies and probabilistic analysis approaches to quantify our test analysis correlation instead of saying, hey, we're in the ballpark. That just doesn't cut it. We also plan to do a full-scale crash test of the Bell ACAP. We also have a flight test article from that test program, and we plan to do a full-scale crash test as well as a fully integrated finite element simulation. Now, all of this sounds great, and you say, well, you've got a lot of test plans, but what do we hope to get out of all of this? And the main product is validated numerical simulations for impact. We also want to come up with recommended approaches for modeling composite materials, human occupant injury and modeling of human occupants, landing gear models, and also multi-terrain impact. It's a big topic because rarely, actually less than 80% of the time, do any aircraft crash onto hard prepared surfaces. And then we also want to improve our procedures for test analysis correlation. And finally, we want to assess our lightweight external deployable energy absorbing concept that we hope to optimize for multi-terrain impact. And last slide. Next slide, please. I hope you realize that I don't do all this research by myself. This is really a team effort. And I am as honored as I am to be here. I'm very glad and very pleased to work with such a wonderful team at NASA Langley. I've listed all the names. I'm not going to read them out to you, but I'm very grateful for all the work that they do to support this research. Thank you very much. I hope to answer any questions that you may have. Thank you.
Thank you, Dr. Jackson. I'm J.D. Harrington. I'll moderate the question and answer session. One caveat before you ask your question, if you'd wait until we get the microphone to you so everyone can hear the question, and also identify yourself before you begin. With that, are there any questions here in the audience? I do have one or two questions as well that were emailed to me, but we have one here in the front.
Okay, Karen, I get concerned when I see in the 1990s that we had correlations that were in error for, I don't know, about 30 to 40 Gs, which I guess is a significant difference to cause very high injuries. What is the current state of the art of those correlations if we were to repeat those crash analysis for the helicopters with modern computer resources and all the elements that you could afford?
That's a sort of a tricky question. We had to deal with the situation that we were dealing with at the time. If we were to do it differently today, we would definitely have more elements than 10,000 elements, or as it ended up, we had about 6,600 elements. That's not enough elements to have an accurate simulation, probably. And we would need to do a mesh density study. We would probably need to do some testing where we went out and pulled little pieces off the airframe and did testing to get a better idea of what the material properties were. Let's see. I've always said that if you know the geometry well and you can simulate it and mesh it, if you know the material properties well, if you know how the input conditions, you're going to do a pretty good job in predicting the response. And subsequent to this helicopter crash test and simulation exercise, we've done a much improved job of predicting the response, the initial failure and progressive failure of composite material. So I would say we would be doing a much better job today than we did in the past.
I guess I was trying to get to the point of whether it is mesh resolution that is the limiting factor in predicting things correctly, or is it mesh resolution, or is it that the fundamental physical models are not accurate enough? So what are the high poles in the tent?
Both. In the case of the ACAP simulation, both were a problem. We did not have a real good mesh density at the time. We need to improve the mesh density. These are fairly simple elements. In and of themselves, they're fairly simple formulations. They're not high order elements. They're very simple elements. And so you have to have a lot of them to get a very accurate response when you're predicting crushing and deformation of structure. So at the time, that we did this, that was the best we could do. I think things have improved now. So.
All right, another question here in the front.
Yeah, I noticed you spent a little bit of time talking about stroke and a lot of time talking about providing crush paths and crushable material and all that, but it seems like, I don't know if I know how to phrase this exactly the right way, at the end of the day, for a given impact velocity, you're limited by a kinematic condition on the stroke. Now, obviously, if nothing's, if stuff's not going to crush for you in the right way or not going to soak up energy, then you're not using your stroke. But it seems like a lot of, whether you're talking about landing a CEV or protecting occupants of a helicopter crash, you've got to provide a stroke path that you can use, because for a given impact velocity, the G's are going to be hard limited by the length of stroke that you provide. And I didn't see or didn't hear you going into that. I mean, that's a geometrical design consideration.
Yes, it is. Velocity equals 1/2 2gs, where S is the amount of stroke that you can have. And so those two are inextricably tied together, and you have to provide that stroke. If it's insufficient, then the acceleration is going to be higher than you would like. That's just the world we live in.
Yeah, I mean, if the CEV seats have 6 inches of stroke available, and that's all the stroke that's in the cabin anywhere, then you can have any kind of energy-absorbing material you want, and you're going to be hard limited on Gs.
That's why we're spending so much time looking at external devices, like airbags, looking at landing legs that can deform and stroke. All of those external devices lower the velocity that then gets input upon impact of the test article or of the CEV onto the surface. It's also true that, for example, looking at multi-terrain, water is a great energy absorber. You know, when you impact into water, it deforms beautifully. Also, soft soil does similar things. But those are different kinds of loading situations than onto a hard surface. So it's very important, and you're absolutely correct, that those two things are inextricably tied together.
Okay.
Yeah.
Any other questions here in the audience? Like I said, I have one or two here that were emailed to me before it began from people that couldn't attend. Dr. Jackson, many of the crash tests that you shown in your presentation and that are from designated heights and specific speeds and that. But how do you ensure that they accurately reflect real-life conditions, which may involve accidents from much greater altitudes and higher speeds?
It's a good question. Essentially, the early crash test programs were performed at very high impact velocities, and these were determined to be non-survivable by looking at the occupant responses. So the idea is that you have to look at what is the survivable envelope and then try to incorporate features that push that envelope out. So if you have a very high velocity impact, let's say an airplane flies into a mountain, you're just not going to be able to protect those occupants in that case. And interestingly enough, that over the years, as time has gone by and more crash-worthy features have been incorporated into military helicopters, we're finding now that accidents are occurring at higher velocities and the occupants are walking away as a result of the features that are being incorporated. So it's every test is different. There is always a reason for choosing the impact conditions, and I would say that you know, at higher and higher velocities, then at some point you reach a point at which the impulse that's input into the structure is too high to provide protection for. So, that's
okay. Any other questions? You're in the front here.
Often the impacts, especially if you're going to hit an irregular terrain, there are multiple impacts. There's a bounce and a bounce, where you've used up or destroyed possibly your stroke and your impact on the first. What are you doing to take a look at those cases where you have two hits and not one when you actually crash?
Well, right now we're really focusing on that initial impact with the recognition that secondary impacts do occur and are important. And we're hoping that all of the energy is not used up during the initial impact so that some is left over for the rebound and for the secondary impact that occurs. And this is, like, for example, during the ACAP crash test, that honeycomb was 25 inches long, and during the test we had about 12 inches of deformation, which meant that if there was a secondary impact, there would have been some left over to provide some support for that. But we don't spend a whole lot of time looking at secondary impacts, except for that case of the Lear fan, in which we wanted to put that longitudinal pulse in to look at the response of the side-facing seats. But it is an important factor as well.
Isn't there a tendency also, though, because of the frictional forces, that when you have that secondary impact, you tend to turn linear motion into rotational motion, which can be even more complicated?
That can be true. It can be true. It depends on the stability of the system and how high the CG is. And you have the initial impact, and then if there's an overturning moment, then that's what will happen. And that's what you saw with for example, the F-111 crew module. The initial impact, the energy absorber wasn't sufficient to really slow the vehicle down or the crew module down, and so it started flipping over. So you saw that.
All right. I have one more question, and then we'll go to back out to the floor here. A lot of the technologies that you've shown here, is it possible to integrate that into the current fleet that's already in motion, or is this just primarily for new designs still on the drawing board, so to speak?
Well, a little bit of both, actually, to answer the question. Some of the designs, for example, the external energy absorber concept, could be used on existing designs that are out there now. In fact, the Navy is looking very hard at external airbags because most of the military helicopters that are flying today were designed for impact onto hard surface. What happens when those helicopters impact on water? And so they wanted to come up with some kind of device that could be applied externally that would lower the impacts that have the impact velocity to the occupants during a water impact. So they look at airbags. We could look at our external composite honeycomb concept to do the same types of things. The optimal approach will always be to incorporate crash-worthy features up front during preliminary design using a systems approach. And if that's not done, then you're faced with either a retrofit or looking at some other type of device that might be added externally. So.
Okay. We have a question here in the back.
I was just curious whether if NASA's expertise and its modeling tools were used by NIST in their investigation of the World Trade Center Tower, the collapse that was brought about by the impact of the aircraft.
Yes. We didn't actually do that simulation. However, the code that we use, LS-DYNA, was actually used to do an assessment of the World Trade Center accident, and that was actually reported in the LS-DYNA Users Conference a couple years back. Yes.
All right, are there any other questions? All right, then that's going to conclude our presentation today. I'd like to thank Dr. Karen Jackson. Thank you very much. If you have any more, if you'd like more information about any of the aeronautics programs, please visit us on the web at www.aeronautics.nasa.gov. Thank you very much.